Okay, good morning, everybody. Please do type your name in chat so I can get the attendance. Do you have any questions before we start up? Getting behind. Okay, we've been going a little bit slowly at the beginning just to get over the humps of connecting by this fairly unfamiliar mechanism. Even if you did this last spring in your classes, it was in a context where you knew what to expect, you knew the instructor, you knew other students, and here we're starting from scratch, so it takes a little bit to get going. Don't get behind. This is not a course where you can just wait until the test and then study and be okay, because everything builds on everything else. So what we did in chapter 1, chapter 2 builds on that, chapter 3 builds on that, chapter 4 builds on that. So this is a very very vertical progression, and so if you get behind, you're going to be in trouble. So if you haven't done the homework, you're behind. If you didn't take the quiz, you're behind. If you didn't get at least a 7 on the quiz, you're definitely behind. So start now and catch up if you're behind. There are lots of resources. I have office hours. There are help sessions with Jacob. If none of those times work, email one of us. We'll try to find a time to work with you that meets your schedule. But take the initiative and ask for help to get caught up. If you're getting less than 73% or 75% or so on the homework, you're also behind. The way homework is structured is that there's some really easy problems at the beginning that are very straightforward, sort of basic, and at the very end there's some challenging problems. And so the basic problems help you consolidate the basic ideas, and the challenging problems are intended to really make you think about applying them. Students who get less than 75% routinely on homework typically don't pass the course, by which I mean get at least a C. So homework is really important. If you think that you know things too well to do the homework, then it should take you very little time. So do it anyway and stay connected. So what are we doing today? So last time we introduced probably the most important thing in the entire course, which is the momentum principle, which relates a change of momentum to an interaction with the surroundings quantitatively by quantifying these interactions as forces. And today we're going to work on applying the momentum principle in various contexts. We're going to talk about predicting motion, using it to predict the motion of a system under a constant force, which is really simple. And we'll also talk about thinking about situations of which physicists call collisions, which are really large forces in short times, and extracting information about things like forces. And then if we have time, we'll talk about applying the momentum principle to predict motion with a varying force, which is actually a more interesting and a more common situation. So that's the plan for today. We've now encountered some things, some big ideas that it's important for you to be on top of. So things that should be in your notes. What are these? Well, the most important thing is fundamental principles, and we now have one. We have a fundamental principle. The momentum principle. And that says there are various ways to write it, but one is to say the momentum short time in the future depends on two things. It depends on the momentum now, or the momentum this instant, I like to say, we can also call it, plus the net interaction with the surroundings over a short time delta t, expressed as the net impulse, which is the product of the net force acting on the system times the time. So this is something you need to know. And there are various ways to rewrite this if we reorganize it. What do I mean you need to know? You need to know it because although you'll get equation sheets for quizzes and tests, this will not be on it. This is something so fundamental that if you don't actually know it, we can't have conversations. We can't really work together, so it's important to know it. There's some definitions that go along with this. So there's some definitions that you also need to know. There is, first of all, the definition of average velocity, which we got from chapter 1. So average velocity is displacement divided by time. And that leads us to a position update equation where the position a short time in the future is equal to the position this instant plus the average delta t. So that update form looks a lot like the momentum principle. And there's also a definition of momentum, which is equal to gamma times mass times velocity. Gamma is equal to 1 over the square root of 1 minus the speed over the speed of light squared. And gamma is approximately 1 if the speed of whatever we're talking about is much less than the speed of light. And we also talked briefly about something we're going to work on today, which is iterative update of force, momentum, and position. And we use a scheme where we find the net force acting on something. If it's a constant, that's easy. If it's not a constant, or if there's more than one force, we have to actually do a little work. We use that to update the momentum of the system. We use the new momentum to update position. And now that we've got a new position, we see if the force has changed. We repeat and we do it again and again. This is a very general approach that's useful in a wide variety of circumstances, whether the force is constant or varying. Okay, these are things you need to know for quizzes and tests. So let's try an example using this update. Using constant force. Using constant force is easy mathematically, but that's actually pretty unusual in the real world. We'll do this with a constant force, and we'll see later on, we may have an experimental lab with constant forces. But really in the real world, forces change. And so even something simple as a ball moving through the air, the force on it is typically not constant because the force by the air depends on the speed of the ball. And so if it's a large force slowing the ball down when it's moving fast, and it gets small when the ball is moving slowly and the direction is opposite to the ball's direction. So in the real world, constant force is really an unusual situation. However, it's a good way to get started. So let's imagine the following situation. We're on the moon where there's no air and hence no air resistance. And we're going to kick a ball. Okay, so we're going to predict a motion of the ball. So near the surface of the Earth, you probably know that the that the magnitude of the force exerted, the gravitational force exerted by the Earth on an object near the Earth. So the magnitude of the gravitational force on an object is equal to the mass of the object times g, where g is the magnitude of the Earth's gravitational field, and it has the value of 9.8 newtons per kilogram. The mass of the moon is different, so this force is different on the moon. On the moon, g is about equal to 1.6 newtons per kilogram, which means that someone walking around the surface of the moon is attracted much less strongly to the surface of the moon and therefore can jump higher. You may have seen films of astronauts on the surface of the moon. So on the moon, you kick a ball of a mass 1.25 kilograms with an initial velocity of 15.0 meters per second. So you kick it, so it's going up in the air in the y direction and also in the plus x direction. And your initial position is, according to, relative to some origin, is minus 140.00 meters. So what's the path of the ball? So what we're going to do to figure this out is we're going to apply this iterative update procedure. We're going to find the net force, update the momentum using the momentum principle to do this. So momentum principle. We're going to use the new momentum to calculate an average velocity, use that to update the position and take steps of a second. And we'll see what happens. Now, this is just going to be a lot of calculation, and I personally don't feel like doing that by hand, so I'm actually going to write a little VPython program to do that. So as usual, here we are at glowscript.org. So let's write a program together. So we're going to call the program ball on moon. So we're just going to use glowscript as a calculator to do this repeatedly. So the mass of the ball, we said, was 1.25 kilograms. We can't put units in here in glowscript, but we're going to just make sure that we're using SI units all the time. The value of the moon's gravitational field is about 1.6 newtons per kilogram. And we wouldn't actually have to make an animation. We could just do this without an animation, but it might be kind of neat to make an animation. So we'll make a sphere to represent the ball. Its position is a vector, and we said minus 140.00 meters. Its radius, we better make it big enough to see, so 0.5 meter. We'll give it a color, make it cyan, and we'll tell it to leave a trail so we can see. So we'll do make a trail. Now we need some initial values. The initial value of the velocity is vector. We notice that we can abbreviate vector here. We don't need to type it out. It's something we type so often. And the momentum is m times v here. And we need, so we're going to need a time step. So we'll have a delta t equals 0. And now we need to to do some calculations. So we're going to calculate the net force is just going to be the gravitational force. And so that's going to be equal to, it's acting in the minus y direction. So that's going to be equal to 0, and the x is a vector 0 minus mass times g, because it's in the minus y direction, 0. And now we're going to use this update form. So the momentum, the new momentum is going to be equal to the old momentum plus F net times delta t. And now we're going to approximate V average is equal to P divided by M. So we're taking the final value of the momentum and setting it to that. And then we're going to have to update the positions. So we're going to say ball.position is ball.position plus V average times delta t. And we'll just, and we could print some things. But now we've only done this once. So we could do this. We can print ball.position. In fact, let's print some text so we can see what we're printing. We'll print position in quotes and then ball.position. And so if we run this program, what it's going to do is we see a little teeny dot for our ball, and it just prints the position once. But we want to do this more than once, so we need to do this in a loop. Is there ever going to be a question where you need to use VPython to find the solution, or is it always optional? There could well be a question where you need to use VPython to find the solution, but we're not there yet. Okay, by the end of the semester in lab, you will, certainly the lab practical will actually have some questions on it. Now, that said, there are plenty of situations where you want to use VPython to find the solution, because vector calculations are really easy in VPython and they're really a pain with your calculator. So most people get into the habit of actually using VPython as a calculator to do their homework. And so if we just said take one step, this is actually an easy way to do it. And some of the virtues are that you can see if you made a typographical error. Suppose you had typed the initial velocity wrong. You discovered that you had typed v equals 13,15,0. You'd have to go through all the calculations on your calculator again. But here, all you have to do is just retype. Suppose we had gotten 13,15,0. And we change it to 15, okay? So let's print the momentum to so let's see what it says. Okay, so that's momentum. So what we really want is to do this in a loop. So we're going to have to put a condition to end the loop. Well, let's say while ball.position.y is greater than 0. So as long as it's still above the surface of the moon, which we haven't bothered to draw in our little program. And I can select all these lines and just press tab to indent them all at the same time. And now let's see what happens here. Okay, so what is going on? Oh, because delta t is equal to 0, which was absolutely not what we needed. Of course, we're going to get 0. So let's try this, and we're still not getting anything. So let's.
As far as I can tell, the position you say is, well, delta y is greater than 0. Well, we're at 0, so it's not going to be greater than 0 in this case.
Good point. Thank you. So let's actually let's make it greater than minus 0.1. How about that? Good call. And that didn't look right. So let's actually put some pauses in here. And let's put a print statement in here so we can see what's happening. So we're debugging together. There we go. So I'm just clicking at every time step, and we're updating the position and the momentum at every time step. And you're probably not very surprised to see, yes, you're right, Seth, that was exactly my problem. We did need a rate statement. But if we have this scene.pause, then we get to draw the picture. So we can replace this by, if we want, that's actually kind of informative. So we'll make it rate and or something like that and comment out the scene.pause. And now it'll run printing out values. And we see that we have both numerical values and the trajectory of the ball. Okay, I'll post a link in Canvas to this program and to other programs that we've written together during class here so that you can look at them. But you can see that what we did, that this would have been, first of all, kind of annoying to do by hand. And that that what we've done is just calculated a force, updated momentum, gotten an average velocity from the final momentum, updated the position, and printed the results. So that if we needed those results for a homework problem or something, we would have them. So, and we could make this program a lot fancier. We could have done this without any animation at all, by just using, instead of ball.position, we could have just used the variable r. And then we wouldn't have gotten a picture, but we still could have printed things out. The pictures are often, the visual display is often very useful for debugging because it shows you what it's not doing the right thing. So that's a particularly productive thing to do. So this is an example. Now, notice that in this particular case, because we had a constant force here, we're always calculating exactly the same thing inside this loop. It's not changing at all. And you may think, why do I put it inside the loop? Because it's not, doesn't need to be updated, doesn't need to be recalculated, only things that need to be updated go inside the loop. And it's true in this case, we didn't have to. Now, it's not adding very much overhead, so it's fine. But in most cases where the force is changing, we will have to be updating it inside the loop. So I'm just doing it because it's a good habit always to put it inside your calculational loop, even if it's actually just a constant. Okay, so that's one thing we can do with position momentum update. What else can we do? Well, another thing we can do is actually deduce forces. So let's see an example of a situation where we could figure out a force. So what we're going to do here is deduce a force. This is This is often useful in situations of what we call collisions, which are interactions that are really strong over a very short time. An example of a collision is something running into something else, a ball bouncing off the floor, a stick hitting a hockey puck or whatnot, because during that time, the interaction force is stronger than almost all forces from anything else in the surroundings, and we can neglect them. And they usually last a very short time. So it's reasonable to assume that the force is roughly constant. So let's consider a situation in which we have a collision, and we're going to estimate the force involved in the collision using the momentum principle. So our situation is this. We have two students who are late to a class, and they're both running to class, and they're not really looking where they're going, and so they run into each other, collide, and come to a stop. And the question is, how big a force did student 2 exert on student 1? Well, in order to apply the momentum principle, we're going to use delta P is F net delta T. We need to do various things. We need some numbers, but the first thing we actually have to do is choose a system. And for this, we're going to choose one student as the system because we want to estimate the force. We want to know the force exerted by the surroundings on that student. If we take both students as the system, then we can't figure out the force by the surroundings on them. So what we're going to do is choose student 1 as the system and student 2 as the surroundings. And then we can say the change of momentum of student 1 is equal to the net force exerted by student 2 times the time the interaction took. So we are going to need some numbers, though. So we're going to need a mass. So let's say this mass of the student is 60 kilograms. Okay. And now we need a speed. So let's think about a reasonable speed for someone to be running. An Olympic sprinter can run 100 meters in about 10 seconds. So they can run 10 meters per second. These students are probably not running quite that fast. So, but they're in a hurry. So let's say their speed's 6 meters per second. And let's assume that the students have identical masses and they're running at identical speeds, because our goal here is just to get an order of magnitude estimate of the force, which we don't know. It could be big, it could be small. And so now we're also going to need a value for delta T, the time of the interaction. So the time, and the time of the interaction is defined from the beginning of contact here, beginning of when the force is exerted, till the end of the interval, which we're going to define as which we said the students run together and then come to a stop. So we're going to define it as the time from initial contact to coming to a stop. And for right now, let's just assume that it's 0.02 seconds, 2/100ths of a second. We'll see in a minute how we can actually estimate that using ideas from chapter 1. But for right now, let's say it's about 2/100ths of a second, which is a short time. Then we can say, okay, so the change in momentum is equal to the final momentum of the student. Now, what's the final momentum of the student? Well, their final velocity is 0, 0, 0. They came to a stop, so their final momentum is just 0, 0, 0. And what was their initial momentum? Well, that's more interesting. This student was running in the plus x direction. So it looks like their momentum was 60, here, let's do it this way, 60 kilograms times 600 meters per second. And that's going to be equal to the net force times delta t, so that's going to be equal to the net force times 0.02 seconds. And so we have F net, we can solve for F net, and we get 60 times 6 is 360, so we have a minus 360 kilogram meters per second divided by 0.02 seconds, which gives us a force of negative 18,000 newtons. Now it sounds big. The magnitude of the force is 18,000 newtons. But how big is it? What can we compare it to? Well, just for comparison, we can compare it to the gravitational force on the student near the Earth, which would be the mass of the student times g, which would be 60 kilograms times roughly 9.8 newtons per kilogram. We're estimating things here, so we'll say 10 newtons per kilogram. So that's about 600 newtons. So this is actually a lot bigger. This is a huge force, right? So it's actually 30 times larger, 30 times the force of gravity, which is a huge force, which is why collisions can do a lot of damage. Okay, so how could we have estimated delta t here? Most people, when they're estimating a small time, guess a second. But how do we know? The relative speed, so Seth is asking, why is the relative speed not double, relative velocity double? And it is, if you switch into a reference frame where student one, you're traveling with student one, then it does look like to you like student two is coming at him twice as fast. But we're not in that reference frame. We're in a reference frame where we're standing on the ground looking at both students, and we've chosen student one as our system. And so what happens to student one's momentum in our reference frame is that he is going at 6 meters per second, and then he goes down to 0 meters per second and stops. The principle of relativity, which you may have read about at the end of chapter 1, says this. It says that the laws of physics are consistent and produce consistent results and predictions in any reference frame you choose, as long as it's not speeding up or slowing down or rotating. So any inertial reference frame. But you have to pick a reference frame and stay in it. So it's a completely legitimate analysis to say we're picking a reference frame where we're standing still and these students are both moving. And when we take a video and we analyze the video, we see that this guy, student one, was moving at 6 meters per second. Well, so Alexander says, isn't isn't it the case that since both students are the same mass, it's a zero-sum collision? And this, of course, this is another issue of choice of system. So if we chose both students as the system, so let's consider here that suppose we chose system both students. Then we have momentum 1 of student 1, and we have momentum 2 of student 2, and these momenta are equal and opposite, so that what happens in this reference frame, I mean with this choice of system, sorry, we're still in the same fixed reference frame, is that the initial momentum of the system is equal to P1 plus P2. They're equal and opposite, and so that's actually equal to 0. And after the collision, the total momentum is 0 plus 0, and it's still 0. And that tells us that the net force by the surroundings on both students was 0, 0, 0. But we actually already knew that. I mean, they weren't speeding up in the y direction or whatever. They were going at it. Their initial momentum and their final momentum are the same. It's true, but it didn't give us the information we wanted. The information we wanted was the force one student exerted on the other student. And so to do that, we have to choose one student as the system and the other student as the surroundings. In a different reference frame, the force might be different, and we'll look at that more in chapter 10, actually, when we really talk about collisions. For right now, though, we're going to pick this reference frame and stick with it. So choosing both students as the system does indeed, it gives you a correct application of the momentum principle, but didn't give us the information we wanted. So when you're solving a problem, there's actually some thought that needs to go into deciding what you're going to consider to be your system, what you're going to consider to be your surroundings, which reference frame you're choosing, and then stick with it. And once you stick with it, everything should work out. So I want to go back to how we could estimate delta t. And it takes us back to the idea of average velocity. Let's consider the average velocity of student 1 during the collision. In fact, let's just consider the x component here. Since we're assuming that the force was constant during this time, a reasonable approximation to the average velocity is really the arithmetic average. So we can say it's 6 meters per second, which is the initial speed, plus 0 meters per second divided by 2, and that gives us 3 meters per second. So between when he starts to slow down and he comes to a stop, his average speed, the x component of his average velocity, his average speed was 3 meters per second. Well, we know that working in x dimensions, x final is x initial plus v average x delta t. And so the question is, how far did the student move during the collision? And that depends on delta t. So if delta t equals 1 second, then x final minus x initial is going to be equal to 3 meters per second times 1 second, which is 3 meters. Now, from the time the students first touched each other till the time they came to a stop, did either of them move 3 meters? No. If they had moved 3 meters, they would have had to pass right through each other. So the collision must have taken less than 1 second. So let's try delta t is 0.1 second. Then x final minus x initial is 3 meters per second times 0.1 seconds, which is 0.3 meters or 30 centimeters. And no, the students didn't move 30 centimeters either, which is pretty much the width of the whole student. So if delta t is 0.01 seconds, then the distance the student moved would be 3 meters per second times 0.01 seconds, which would be 0.03 meters or 3 centimeters. And so the question is really, even though students are touching, they're still moving together. So the question is, how much were they compressed? How much was the student's body compressed? And so if we guess compression, a compression of 6 centimeters, then we get a delta t of 0.02 seconds. And so if you have a video of a tennis ball hitting a wall, for example, and you see the amount of compression of the tennis ball between when it touches the wall and when it comes to a stop, you should be able to estimate, and you know its average speed is the speed it had at the beginning and 0 at the end, so to average that, you should be able to estimate the collision time, which is often shorter than you might think. Now it happens that for constant force, this is one of the very few situations where we actually can come up with what's called an analytical solution by applying the momentum principle. What analytical means is algebraic. We can write out a solution of x as a function of time, for example, that we just plug numbers into algebraically. And the reason we can do this is that we can get an exact answer for the average velocity based on the arithmetic average. So remember that we talked about if v sub x, say, varied linearly with time, then the average velocity over some time interval, delta t, really actually is this point in the middle. And so this Vx average would be Vx initial plus Vx final over 2. This is, of course, not true and not useful if the velocity is doing anything else. So if it's oscillating back and forth or something like that, and we pick some time interval, delta t, it's really not necessarily going to be the case that the average velocity is the average of those two. In this case, the average velocity ought to be higher. But in constant force, it turns out that that's actually correct. So V average, we're going to work in the x direction here just for concreteness. X is actually equal to Vx final plus Vx initial over 2, constant force only. So there is an analytical solution. It's not really all that useful because in the real world, there really isn't a constant net force very often. Even if you use this to solve a problem kicking a ball, as we did on the moon, it needs to be on the moon because otherwise the the force by the air is important and varies and changes the motion a lot. So we'll work this out, partly because you may have seen this in a high school physics class, and partly because it's an example of a case where you can solve something analytically. So it's kind of interesting to see that, but it's not something we're going to use a lot. So here's how this goes. We have we're going to talk about a constant force in the x direction. The thing may be moving in the y direction, but it's only affected in the x direction. So the momentum principle reduces to px final is px initial plus f net x delta t. And so we have, dividing by m here, we have the final x component of velocity is vx initial plus f net x divided by m times delta t. So that's after our delta t time interval. And we know that in this very special case, the average x velocity is Vx initial plus Vx final over 2. This is special case. And we can write this out a little bit differently because Vx final, we have an expression for Vx final here. So we'll plug in the line above. So we get Vx initial plus this whole expression, Vx initial plus f net x over m delta t divided by 2, which gives us Vx initial plus a half f over m fx over m delta t. So that's Vx average. So we have P final is P initial plus F net delta T, and of course that's 3 separate equations. Px final is Px initial plus F net x delta T. Py final is Py initial plus F, sorry, not a vector, what's a component, F net y delta T, and so forth for Z. So if we have forces, a constant force operating in both directions, then we could certainly apply that. If the force is 0 in one direction and constant in the other, we can apply that. And that's actually the case we did on the moon. So if we look at just a picture of we look at so the motion of the ball on the moon looked like a parabola, right? So if this is y and that's x, it looked like that. Now, let's think about what would happen if we plotted, so this is ball on moon. If we plot y versus t and x versus t for this, what would happen? Well, the ball started on the ground, it went up, and it came down and stopped. So y versus t did that. that's because there was a constant net force in the y direction. In the x direction, there wasn't any force because there was no air. And so x versus t basically looked like this. It just went at a constant speed, getting farther and farther away from the origin until, I should actually use, since I should use the same t here. So it went at a constant speed until the same end time. And why did it stop? Well, the ball hit the ground. But if there had been a constant force in the x direction, we could apply that in the x direction too. But notice that a force in the x direction doesn't affect motion in the y direction, right? So given this graph for y as a function of t, well, let's do a simpler one first. Let's try to graph the x component of velocity as a function of t. So we know x is a function of t. What is the x component? If we plot the x component of velocity of this ball on the moon as a function of t, what would that look like? Well, x is increasing linearly versus time. So every second it goes the same distance. So that actually means that the x component of velocity here was constant until it hit the ground, and then it went to 0. What about v sub y versus t? So what happened to v sub y? Given this graph of y versus t, yeah, so we have to think of it. The way to do this is to think, what's the initial velocity? Well, initially y is increasing, so v sub y is going to be a positive number because the ball is going up. So it starts with some y increasing here. But in one delta t, it goes up a certain amount. In the next delta t, it goes up less. In the next delta t, it goes up less. So it's actually decreasing with a constant value due to this constant f net. So in fact, v sub y decreases until it gets to 0 when the ball momentarily isn't going up anymore at all. It's y at the very top. The y component of its velocity isn't changing at all. It's instantaneously neither going up nor down. It's at a maximum. So dy dt is 0 here, which is, of course, and dy dt is v sub y. So basically, v sub y is the derivative of this. And then it starts to come down again, and so it's going in the negative y direction, and it comes down again at a constant, speeding up at a constant rate in the negative y direction until it hits the ground. Yep, and so here's where we cross the time axis. So notice you can't graph a vector. You have to pick one component of a vector and graph it. So we can graph y versus t and x versus t, but we can't graph them together, and although if we had another dimension, we could. So we have a little bit of time left. Not enough to finish this, but what we're going to talk about is an example of a force that's not constant. And we're going to be working right away with actually 3 forces that aren't constant. The first we'll show as an example now and just finish this up next time, is the force that a spring exerts on an object that's touching it. But we will In chapter 3, we'll talk about the fundamental forces of physics. There are 4 fundamental forces that sort of form the basis of every interaction that we know about. One of them is a gravitational force, which varies with distance as things get far apart from each other. The other is the electric force, which varies in the same way. There is the strong force, which is what holds nucleons in the nucleus, and that's actually a force where things have to touch. And then there's something called the weak interaction, where things have to be very close, and even then the probability of interaction is low. So most forces do vary with distance, and they're not constant. So what would happen with the v sub y? Good question. So here's the time when the ball hits the ground. So here's our time when the ball hits the ground. So v sub y is decreasing until it hits the ground, and then it becomes 0, doesn't it? So in fact, it's now 0 and nothing's happening, and v sub x is also 0. So at this point, they're both 0. So good question. Thank you. So it turns out that spring forces, though, are a very good model for lots of fundamental forces at the microscopic level. For example, the force between 2 atoms that are bonded together in a solid actually behaves very much like a spring force. It's hard to pull them apart. It's hard to push them together. So qualitatively, when we're talking about the force by a spring, the force depends on the stretch of the spring. And for some reason, yes, the spring force is called Hooke's law, probably because Robert Hooke, an English physicist, was the first to write it down. So what is stretch? Stretch is the difference between current length and the relaxed length of a spring. So you think about a spring. If you just hold it in your hand, it's at its relaxed length. If you pull on it, it stretches. If you push on it, it compresses. So it can go both ways. And so stretch, actually, the force is directly proportional to stretch. So we can write that the magnitude of a spring force is equal to some constant times the absolute value of the stretch, where this constant is called the spring stiffness. So basically, if we have a spring sitting here attached to the ground, this is its relaxed length, L0. If we put a block on it, it's compressed to some shorter length, and if we push down and let it go, it may actually stretch up to some, so this is shorter, this is longer. So stretch actually has a sign. Stretch is defined as the current length of the spring minus the relaxed length. So current length minus relaxed length. And so it can be positive or negative. Here, when the spring is shorter, its current length is less than L0, so stretch is less than 0. And when it's longer than its relaxed length, the stretch is greater than 0. And so on our diagram here, this distance would be the stretch for spring in situation 1, and that distance would be the stretch in situation 2. But this one would actually have a negative sign when we compute it algebraically. So we are going to need, and the direction of the force that the spring is exerting on the block is acting in a direction to restore it to its relaxed length, right? So in this case, the spring is certainly pushing up on the block. And in this case, it's stretched more than its relaxed length, so it would be pushing down on the block. So we want an equation that captures this directionality of the force. We also need to be able to write the spring force as a vector because springs don't just go up and down. So for example, what would happen if we had a spring that was at an angle instead of just standing straight up, or we had a spring hanging from the ceiling that was at an angle? Okay, we need to be able to get the direction of that force by the spring on whatever's attached to it here, even if it's not an angle. So we need a way to write this force as a vector. So what we're going to do is we're going to define a vector L that goes from the fixed end of the spring to the movable end. Now, it's possible, of course, that both ends are movable. So really, it's from one end of the spring to the end where the object we're interested in is. But this is kind of an interesting way, a useful way of thinking about it. And so this vector L, in this case, would just go from where the spring is attached to the ground to the end of the spring. In this case, the vector L would go from the attachment point to the end of the spring here. If the spring is hanging, here would be the vector L, and in this stretched case, that would be the vector L. So the vector L stretches along from one end of the spring to the end where there's an object that's experiencing a force due to the spring. Of course, this vector L has a length. But we don't really want the force to depend on that length. It really depends on the stretch. So the difference of that length and the relaxed length. So what we're going to do is we're going to use a unit vector L hat. So unit vector L hat in the direction of L is just equal to the vector L divided by the current length of the spring, because the magnitude of that vector is the length of the spring. And so we can write the vector L, of course, as the magnitude of L times the unit vector L hat. If we have a spring attached to the ceiling, hanging down here, there's a mass hanging from it. What's the direction of L hat? So usual coordinate system, we have X, Y, Z. So what's the direction of L hat? Okay, what's the direction of L? How will we draw the, yeah. That's exactly right, good. So you guys got it. So the vector L starts at the fixed length, goes down to the mass, and so L hat is a vector of magnitude 1 in that direction. And it isn't going to matter. L hat has the same direction whether the spring is relaxed or compressed, right? So if it's very much extended, L hat is still down. If it's very much compressed, L hat is still down. It just goes from the fixed end to the movable end. So very good, Peyton, Daniel, and Gabriella. You're exactly right. And so we'll finish this up really quickly and come back to it next time. We can write the stretch is equal to the magnitude of this vector L minus the relaxed length. And it's going to turn out that the spring force written as a vector is going to be equal to minus this positive number, the spring stiffness, which is something like 3 newtons per meter, times the stretch, which is positive or negative, times L hat. And we'll start here next time, go back and see why this is true, and then we'll use it. Well, the reason we're doing this is we want to use this force to do the same iterative update of position and momentum, but this time with a changing force as a spring goes up and down. So that's the plan for the beginning of next time. And we'll review this at the beginning of next time.